Hi, I'm Cassie, and I'm going to walk you through question 19 of the AAMC's official physics question pack for the MCAT. So this question asks about how much of an object, specifically an ice cube, would be submerged on one planet versus another. Well, the short answer to this question is that the same amount of the object is going to be submerged, so the same 9/10 of the object is going to be submerged no matter what planet that ice cube is on, whether it's on Earth or the moon, no matter how much gravity any of the planets have. And that's just because the force that's pushing up on the ice cube and the force that's pushing down on the ice cube in the water, they both contain the force of gravity at play. So that gravity just cancels out. Therefore, no matter what the value for gravity is, it doesn't matter. Now, let's get into like a more depth explanation so you can actually understand why that is. Because the concepts tested in this problem, like Archimedes' principle, are really important for the MCAT. They ask lots of questions about submerged objects and objects in fluids. So fluids can be kind of complicated. So let's think about a simpler example than fluids to start that'll help us. Imagine you have a book, and that book is just sitting on a table. Why doesn't that book move up off the table or down into the table? Because there's two forces that are equally at play. You have the normal force that's pushing up on the book, and you also have the force of gravity that's pushing down on the book. And since those forces are equal, the book stays stationary. It doesn't move vertically at all. It doesn't move up or move down. Well, the same concept you can apply to fluid. So when we take our ice cube and we submerge it in the water and it stays floating in one place, it's not moving up or down, right? So therefore we know there must be vertical forces, one force that's pushing down and one force that's pushing up, that are canceling each other out. So the force that's pushing up on the ice cube, we call that the buoyant force. So I'm going to call it FB. And where does that force come from? Well, we know that as we go deeper in water, pressure increases, right? That's why divers have to be really careful when they go too deep in water, because the pressure gets just really strong. And that's essentially because the deeper you go, in water, the more water you have above you, that's pushing down on you, increasing that pressure. So you can think of it like piling up a stack of books. At that bottom book has all the weight of the top books on top of it. Just like the bottom of a pool of water has all the weight of the water that's above it on top of it. So you get a pressure gradient in water, whereby the deeper you go, the higher the pressure. And so that pressure gradient is going to push up on anything that's submerged into that water. Now, how can we calculate that buoyant force? Well, when an ice cube is placed in water, its weight is going to push some of the water that was where that ice cube was out of the way to make room for itself. And when the ice cube takes the place of that water that was there before, it must provide the same upward force that the pressure of the water that was there was providing before. So as a proxy for calculating the value of our buoyant force, we can use the weight of the fluid that ice cube displaces. So I'm going to say here our FB, our buoyant force, is equal to the weight of the fluid that our ice cube displaces. And of course, if we put that in more mathematical terms, we get that our buoyant force is equal to our density. Remember, density is like that funny looking P. The density of our fluid, so in this case, let's say water, the density of our fluid, times the volume of our water that was displaced. So I'm going to say V times F, for the volume of the fluid that was displaced, times the force of gravity. So this is an equation that you can use for buoyant force in these kinds of submersion problems. So now we've covered the force that's pushing up on that iceberg, just like when you have that book on the table, the normal force was pushing up on the book. So what about our force that's pushing down on our ice cube? Well, the force that's pushing down is just going to be equal to the weight of that ice cube, due to the force of gravity. And we know that equation for the weight of something due to the force of gravity. So I'm just going to use W for the weight and then a little I to represent the weight of our ice cube here. So the weight of our ice cube is just always equal to, of course, mass times gravity. So I'm going to say M with a little sub I to remind us we're talking about our ice cube times gravity. So let's fill in our free body diagram here. So what's going to be our force acting downward? That's just going to be the weight of our ice cube here. Okay, so if we were going to set up an equation to understand how these forces cancel each other out, what would we get? Well, always starting with the simplest concept first, right? We've got our force in the upwards direction must be equal to our force in the downwards direction. And in this case, we said our force in the upwards direction is going to be our buoyant force, the pressure of the water that's pushing up, and the force in the downwards direction is going to be the weight of that ice cube. So I'm going to call that again Wi. So now if we go ahead and sub in values here, what do we get? Well, we said we can represent our buoyant force as the density of our fluid times the volume of our fluid times gravity. And then, of course, the weight of our ice cube is just the mass of our ice cube times gravity. So here's the important part for this problem, right? What do you notice? Gravity is in both sides of the equation. In other words, gravity is going to cancel out of both sides of the equation. So that's why it doesn't matter where the ice cube is submerged, on what planet, with what value of gravity. As long as, again, the two forces are acting on the same planet, then you can just take gravity out of the equation whatsoever. Now, I'm not just going to stop there, because if we keep going a little bit further with this equation, we actually find an equation that you can always use to quickly calculate the percent of an object that's submerged in a fluid. So in this problem, they told us that the ice cube was 9/10 submerged in a fluid. But sometimes the MCAT will, instead of telling you how much submerged the object is, they'll ask you to find out, given a certain density of fluid and other variables, what percentage of the object would be submerged in the water. Or they might ask what percentage of an object is above the water and not submerged. Let me show you how we can get an equation that you can use to quickly figure that out. Okay, so if we look at our equation here, we see that we have a density, a volume, and a mass. So always when you're at a point where you're like, don't know where to go next with an equation on the MCAT, you might want to think about other equations you know that you can sub in to the equation you have. So in this case, we have the quantity of density, and we know that density is equal to mass divided by volume. Okay, so then we could go ahead and we could solve for mass. So we'd get mass equals density times volume of an object. And then we could sub in for the mass of our ice cube here. Okay, so let's go ahead and do that. So where we had the mass of our ice cube on the right side of our equation, we now have the density of our, I'm going to say ice cube, times the volume of our ice cube is equal to the density of our fluid times the volume of our fluid. So from here, where can we go? We can get a nice little ratio of the density of our object to the density of our fluid, and we just would have to solve, right? So the first step we could take is, we could solve for, let's say, the density of our ice cube is going to be equal to the density of our fluid times the volume of our fluid divided by the volume of our ice cube. And then we could go further and solve for, therefore, that the density of our ice cube divided by the density of our fluid is equal to the volume of the fluid divided by the volume of the ice cube. And okay, this is a beautiful equation because this is always going to be equal to the percent of an object that's submerged in a fluid. So if you were to plug in values for this equation, you might get something like, let's say the volume of our fluid is 1 and the volume of our object, in this case our ice cube, is 2. Well, that would mean if you got the ratio of 1/2, that would mean 50% of your object, in this case your ice cube, was submerged in a fluid. Now be really careful there because I said submerged, right? Sometimes the MCAT will ask questions about what percentage of an object is submerged in a fluid, and sometimes they'll ask questions about what percentage of an object is suspended above the fluid. So for example, if you had 50% of your object submerged in the fluid, then 50% would be above, right? So be really careful with that. But if you know these quantities, let's say the MCAT gives you the volume of a fluid and the volume of an object, or they give you the density of an object compared to the density of a fluid, you can go ahead and plug those straight in and get the percentage submerged of the object. So this is just a pro tip, a good equation to add to your equation deck so you can quickly solve for the percentage of an object submerged in a fluid. So to wrap things up here, what we talked about in this problem is an example of what we call Archimedes' principle. An Archimedes' principle is the idea that when an object is submerged in a fluid, you have the buoyant force pushing up, and that equals and cancels out the weight of the object, in this case the ice cube, pushing down. So those forces are equal and opposite for an object in fluid to be stationary, to not be moving. And then the other takeaways from this problem, don't forget your equation for the density of an object, that's equal to mass divided by volume. And finally, don't forget about these new ratios we learned that can give you the percentage of an object submerged in a fluid. So I hope this helps. If it helps, give it a like and follow my channel for more content like this.